Welcome to 3321 Mechanics of Solids. I'm Section 1 Instructor Jesse Sanchez. So let's go ahead and get started. Came up with this problem a couple of days ago, and what we're going to be doing, we're going to be drawing the shear and bending moment diagrams. But we're going to do this by the equation method. So let's go ahead and write it down here by equation. So, as your PowerPoint states, we have to get all the reactive forces. As we see, this is a cantilever beam, this is a wall. Cantilever beam, we have a distributed load that goes from 0 to 4 meters, and at the very end we have a point load going downwards with a magnitude of 300 newtons. So, we draw our free body diagram, just a little one, we don't have to go all out. We have 300 newtons at the very end, which will be at point B. And then we have our distributed load. That's 100 newtons per meter times 4 meters. That's 400 newtons. That's actually located right in the center of this 4 meter distance, which basically means this is 2 meters. All right. And the last thing is the reactions at the wall. So you're going to have a reactive force, A, and of course a moment, a reactive moment, which I'm going to call MA. And those are the two that we need to solve for. So let's get started by doing the sum of the forces in the y direction, in which I consider up to be positive, equal to 0. We have positive RA minus 400 newtons, minus 300 newtons equal to 0, and therefore RA equals to 700 newtons. So that is our first reaction. Now let's solve for the reactive moment at point A. This is of course point A, this is point B. The reactive moment at A is done by sum of the moments, but A must equal to 0. In this case, I'm going to consider counterclockwise to be positive. So we have positive reactive moment at A because it is counterclockwise. And then, of course, this 400 Newton force produces a clockwise movement. So that is minus 400 newtons. And it is a distance of 2 meters from point A, and then we have this other 300 Newton force being applied at point B, and it also produces a clockwise rotation, which to our specifications it is considered negative, and that will be 300 newtons, and that one is at a distance of a little mistake here, this is a distance of 8 meters, and that is all, and it should be equal to 0. And therefore, if you do your calculations, this is going to be equal to 3,200 Newton meters. The fact that we got a positive number means that we chose the correct direction for our reaction moment. So these two are very important because from now on, every time we draw a free body diagram for the section that we're interested in, we have to always write down these two. So how many sections can this problem have? Remember that we always draw sections in which we see changes in either external loadings, distributed loadings. So here we have two very interesting sections, right here and right here. So I'm going to call this section 1, and I'm going to call this section 2. So let's go ahead and start from left to right, and we're going to slice this somewhere between 0 and 4 meters. In other words, between point A and point C. We're going to make a cut. And that will be our section 1. So we're going to draw part of that beam. Where we cut, we don't know. There you go. We just know that we made a cut somewhere here, not exceeding C. That is the main point. We still have that distributed loading. And it is still 100 newtons for every meter. We have my reactive force at A, which has a value of 700 newtons. And we have a reactive moment at A as well, which also has a magnitude of 3,200 newton meters. So, there is no forces in the X in this one. We could have seen that over here. If we would have put a reactive moment in the X direction at point A, you would have noticed that because of the external forces, there are none in the X direction. That would have been equal to 0. So therefore, we did not put it in there. And we don't put it in here as well. So normal force here does not exist as well because there's no forces in the X or reactive forces in the X. So if you remember from your PowerPoint, it stated that the shear, the internal loading, we always want to make a clockwise rotation. Always, 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 always. And also, our moment. We want to make this into a happy face, right? So if you cut the right side of this beam, that will go clockwise to make a happy face. If you cut the left side of the beam, it will go counterclockwise for you to make a happy face. And then we do our, here we go, dimensions. What dimensions? Some dimension X. In other words, from here we're going to cut some dimension X, in which X's are unknown. But we just know that this has to apply only from 0 to 4. So remember, this is very important. This can only apply from 0 to 4. So from here to here, it is a distance of X. All right. Well, let's go ahead and solve for the shear. And we do that by taking a sum of the forces in the Y. Must be equal to 0. I consider up to be positive, and we start from left to right. And of course, our very first force in the Y will be this RA, this reactive force. That will be positive 700 newtons. And then we see this distributed load. But this distributed load can be, here you go, replaced by a resultant force. A resultant force that has a magnitude of 100 newton meters for this length. So this is actually 100 newton meters multiplied times X meters. So we're going to leave it as such because we don't know what X is. Over here, for example, we knew that X is 4. So the force that was applied right here is 100 times 4, which is 400, right in the middle. Here, we do not know how far we cut this. We could have cut it 2 meters, which is right around here. We could have cut it 3. We could have cut it 4. So we do not know. So we leave it as a variable X. We just know that X is somewhere between 0 and 4. So we're going to write this in terms of X. So our force is 100 newton meters times X. And it is a downward. So therefore, it's negative 100 newton meters times X meters. And then our last one will be our V, our shear, which is also facing down. So minus V, this must be equal to 0. If we put our B on the right side of the equation, it becomes positive. And therefore, that will give us our equation for shear. All right, that will be V equals to 700. And I'm going to write this since basically your meters right here simplify, or as most of you call it, they cancel each other. This will be negative 100x. And the quantity for this is, of course, newtons. So this is our very, very first equation. This equation will be the one that will be used to graph our shear diagram, which will be coming up closer to the end of this problem. Okay, so let us continue. Let's move this up. And now we're going to solve for the moment equation. So we have the shear equation. Now let's solve for the moment equation. Again, we're still talking about section 1, this section right here. So the moment equation, we have to do a sum of the moments about this point where we made our cut. We could actually do sum of the moments about this point right here. It's not necessary. We can do it from this point right here. So the sum of the moments about this point, which I'm just going to call point, must be equal to 0. I am going to consider a counterclockwise moment as positive. And again, we can start from left to right, from right to left. So let us begin with this one right here. This is a free vector, and it is the reactive moment at A. And it is counterclockwise, therefore it's positive. So we start with a 3200 Newton meter, and it is positive, so I leave it like that. And then we have this force right here, which is the resultant force of this distributed load. It has a magnitude of 100x newtons, and it's also producing a counterclockwise movement, which is positive. So this is 100x, and it is newtons. And now we need the distance at which is being applied. This moment does not need a distance because it's a moment. This is a force producing a moment, and therefore we need the distance from the axis of rotation or the point of interest that we want. So we need to find out what this distance is. Well, this distributed load is a rectangle. It is applied in the center of the rectangle, or the middle. If this distance is x, that means that this distance right here is x over 2. And that is the distance that we're interested in. So we multiply times that distance, x divided by 2 meters. So as you can see, our units are Newton meters and Newton meters. We keep going, and then we see our very last one, and that will be our moment. It is also counterclockwise, so it is plus m, and this is, of course, equal to 0. We're going to solve for this m right here. And I apologize, do not get confused, this small m that stands for meters and this big M that stands for the moment. When we solve for m, we basically have to switch these two to the right side of the equation. So whatever is positive becomes negative, and likewise. So our moment equation, again, only valid from section 0 to 4. It is equal to, this is negative 3200 Newton meters, and of course negative 100x times x over 2, which is basically x squared over 2, and it is also in Newton meters. Another way to simplify this equation is by writing minus 50x squared, because 100 divided by 2 is 50. Let's go ahead and do that. I always like to put my second degree polynomials in descending order, so this will be negative 50x squared, and then of course, oh my goodness, I can't believe I forgot. We need to do the 700. That 700 is also producing a moment. Wow, it's a good thing I caught it, right? So 700, it's producing a clockwise rotation, therefore it is negative 700 newtons, and it is a distance of x from here times x meters plus There you go. So this is what we are missing right here. And of course, this negative 700x, when it goes to the right side of the equation, becomes positive 700x. And last but not least, our negative 3200 that we were missing. Again, guys, I really want to thank you for your patience, especially this being my very first video. You tend to get a little bit jittery and mumble your words, but I'm getting there. Don't worry. I'll be Steven Spielberg by the end of the semester. He's not an actor, he's a director, but he demands perfection as well. I'm just going to box these two up. Well, perhaps. We'll keep coming back to this one right here. Okay. So let us continue. Our continuation goes on to number 2. We're going to be analyzing what's happening in section 2. So we're also going to make a cut here in section 2, somewhere in there. We're going to add everything else over here that we know, and then we get to draw a shear and a bending moment and find out the equations of those two. So let's go ahead and draw that. There you go. We did originally have a distributed load. And since I already know that that distributed load, it is 100 newtons per meter, and it is through an entire distance of 4 meters, I'm going to go ahead and replace this in another drawing with one resultant force. But not right now. Again, I want to take my sweet time, baby steps, and show you everything that is happening. My reactive force at A, going up, 700 newtons. My reactive moment at A, MA, which is 3,200 Newton meters. And then, of course, this distance right here, we keep increasing. This X goes all the way up to here. And again, where did we make that cut? Somewhere between 4 and 8 meters, somewhere in between. So we don't know if it's 5, 6, 7, or 8, so we just call that distance X. All right, which pretty much makes this distance from here to here X minus 4. We did not have to do that in the previous problem because the distance is just X. We did have to account for this X divided by 2 as half the distance. So again, this is 4, this is X minus 4. We don't know what that distance is because we don't know what that X is. And again, this is valid from 4 to 8 meters. Again, only valid from this range right here. All right. Now, let's go ahead and draw our shear. We always want to make the shear so that therefore it causes a clockwise rotation. And then we want to draw our moment that makes a happy face. So it makes you draw a moment, happy face. Man, my hands look old. Okay, disregard that. All right, so let's go ahead and solve for the shear equation. And that is done by doing the sum of the forces about the y-axis, in which I consider up to be positive. This is equal to 0. And we begin from left to right. We see RA 700. This distributed load is 100 Newton per meter, which gets replaced by one guy right in the middle, which is at 2 meters. Since this is 4, this is 2. And 100 times 4 is 400 newtons. So we no longer have to be applying this. This substitutes that. All right. So since this is facing down, this is negative 400 newtons. We continue, we continue, we continue. We see a negative V, and that is equal to 0. So what is our V? V, in this particular case, is, since this is negative, if we flip our V to the right side of the equation, it becomes positive. And this is plain and simple, 700 newtons minus 400 newtons which is equal to 300 newtons. So it is a constant. All right. We're going to also box this one up just like we did the other two, this one and that one. And let's go ahead and also solve for our moment equation. And that is done by doing the sum of the moments about this point right here. That point right there. They must be equal to 0. Counterclockwise is considered positive. And of course, we start from left to right. We have a positive 3,200 Newton meters because it is counterclockwise. We have this RA, which it almost slipped my mind on the previous problem. This is producing a clockwise rotation. So this is a negative 700 newtons times a distance of, from here to here, is a distance of x. And then now we have this 400 Newton force. This 400 Newton, this is producing a counterclockwise movement from this point. So this is plus 400 newtons. And that one in particular has an interesting distance. What is the distance from here to here? So we know this is in the middle, so this is 2 meters. This is also 2 meters. But from here to here, it's x plus 4. So the distance from here all the way to my 400 Newton force, it's 2 plus x plus 4. And of course, 2 plus x plus 4, I'm sorry, minus 4, my bad. Again, I'm a little bit nervous. 2 minus x minus 4, it's really x minus 2. And that's what we write right here, x minus 2 meters. What else? Nothing, 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 nothing. Our very last one will be our moment, m. And it is counterclockwise, therefore it's positive, and this is equal to 0. Sorry about that. Let me move back to the center again. I hope I wasn't off the screen. All right. So when we solve for this m right here, we leave it alone because it's positive, and we pretty much flip everything else to the right side of the equation. So we end up with negative 3,200 Newton meters. This is negative, so it becomes positive, plus 700 x Newton meters. And this right here happens to be positive, so we make it negative, minus 400 x minus 2 Newton meters. Now we can use the distributive property right here and multiply this times this times that to clean it up, or we can just leave it like that for the time being. I think I'm going to clean it up. So m, sorry, I keep capital M, equals to negative 3,200 Newton meters plus 700x Newton meters minus 400x Newton meters minus negative times negative is positive, 400 times 2 is 800 Newton meters. Let's collect like terms. There you go. And then this one and this one. So my capital M is equal to 300x, and that is positive, minus, we subtract these two. That will be 2,400 Newton meters. There you go. Okay, let's go ahead and box this one up. And again, both of these equations, here is the range of x that you can use, or I should call it not the range, but what do you call the range? Domain, the domain of x. All right. Let's take out another sheet of paper. and make our graphs. So I like to bring this drawing over here. There you go. So that way we can draw. Tape this in here so it doesn't move. We can draw. So I'm going to pause it for a second, and by the time I unpause it, you're going to see two graphs appear right below it. Alright, not the straightest of graphs. Over here my device moved a little bit. Our very first one's going to be our shear graph. Its units are in newtons. Obviously we have 0 right here. Our bottom one's going to be our bending moment diagram, and our units are Newton meters. As stated before, you always want to make very faintly dotted lines wherever those sections meet. Obviously we only have 2 sections, so we have one at the very beginning, one in the middle at a distance of 4 meters, and the other one at the end at a distance of 8 meters from A. I'm going to put a little 4 and a little 8 over here. 8. Alright. Now, let us take a look at what's happening here and here. And by that, we go back to our first equations. In our shear equation, we're going to get our shear equation, which is basically V equals to 700 minus 100x. And we're going to create a table. Very nice table. Remember that our range, I call it range, in reality our domain. Our domain is 0, 1, 2, 3, and 4. So we get our calculators and find out those values right there. Alright, so at 0 we get a value of 700. This is obviously a linear equation with a slope of negative 100. So at 1, that's 600, 500 at 2, 400 at 3, and 300 at 4. So let's just say this is right here at 0. This is 700. So that's around 350. So I'm going to come to that point right there. Again, it is linear. So let me take some type of straight object, this handy dandy pencil, and we go do this line right here. And this makes perfect sense because in reality, remember that we always start at 0 and end at 0. Our reactive force is the very first thing that happens. And our reactive force is aimed upwards. That's RA, and it has a magnitude of 700. So it takes us from 0 to 700. So this distributed load, which is basically a rectangle, it becomes a negative 100x equation, and it takes us all the way down to 300. All right. Let us continue here with the shear diagram. And we're actually going to be using the other equation for the shear. This right here. It is a constant of 300 meters. And again, this is for section 2, which is valid from 4 to 8. So remember, we're going to 300. Obviously, there's no need for me to create a table, but 4, 5, 6, 7, 8. When it is a constant, it is a constant. 300, 300, 300. But if you get into the habits, you start noticing that sometimes it becomes helpful. There you go, right here. And where do we end up? Right there. That 300 Newton force being pushed down is my 300 Newton force being pushed down. Right and we end up back at 0, guys. That's exactly what we want. Pretty neat, huh? We start at 0, we end at 0. So that does it for our shear diagram. Let's go to our slightly more complicated moment diagram. And it's just a matter of us creating a table. Our very first one is from 0 to 4. And our moment is being governed by the equation of our very first moment equation. This is really long, complicated one, but luckily we have calculators for that. You're going to notice that the very first one, when x is 0 and 0, we basically get negative 3200. So it's not a problem. So let's go ahead and write down this equation. Oh, I think I'm going to write it down here on the bottom. Equals to negative 50x squared plus 700x minus 3200. All right, don't think this is an x squared. This is just being divided by 2. So they're independent. All right. Expect to see better videos next time, guys. Again, not bad for my first time, I think. So we'll use our calculator to solve for the rest of these. And let me go ahead and pause momentarily. All right. Continuing here. When x is 0, which is right here, we have a value of negative 3200. Let's say 3200 is right here. Negative 3200. Which will make this about a negative 1000, negative 2000. There you go. When x is equal to 1, this is negative 2550. When x is equal to 2, this is negative 2000. When x is equal to 3, this is negative 1550. And when x is equal to 4, we get negative 1200. All right. So at 4, we get negative 1200, which is around right here. And obviously, the fact that this is a quadratic equation, second degree polynomial, we have basically a parabola. Now the question lies, does it curve this way, or open downward, or open upward? So if you plot some of these points in there, for example, the right smack in the middle will be 2, this is 1, this is 3. We know at 1 is 2550, which is around here. 2 is 2000, which is about here. And then 1550, which is here. So we look at this right here. Somewhat of this curve, which makes perfect sense, because if you think about it, this is a parabola that opens downward. And the fact that this is a negative 50x squared, that's basically what it's telling you. It opens downward. If it's a positive 50x squared or an x squared, that one opens upward. All right. So let's go ahead and write our equation for our moment equation for section 2. Let's go section 2. You guys should have that on your notes. That equation's a little bit easier. M is equal to 300x minus 2400. And of course the units are Newton meters. And we're going to be creating also a table for this one. And this is from 4, 5, 6, 7, and 8. So this is something very interesting that you should see in these particular types of problems. On the very first equation at 4, it is a 300. And on the second equation at 4 is also 300. On this equation at 4 is negative 1200. This is for a moment. And what do you think is going to be this number? Well, 300 times 4 is 1200. 1200 minus 2400, negative 1200. Well, what do you know? Where we left off, we begin. So they make sense, don't they? That's pretty neat. So to this, we're going to be adding, basically, since we're starting at 1200, our slope is 300, we're going to be adding 300 every time. So negative 1200 plus 300, negative 900, negative 600, negative 300, and 0. So this is a linear graph. It's a line, and that one goes straight from here to there. Not the straightest of lines, especially working at an angle. So there you have it. This is your shear diagram, your moment diagram. This point right here, point of interest, it is negative 1200. You should always write your points of interest, such as this one right here. And I think that pretty much concludes this problem. Just a quick note. Remember that this problem originally started by having a reactive moment at the base. And what was that reactive moment, if you ask? That was 3200. So the base is reacting with 3200, right? So there's two ways to look at it. It's 3200 counterclockwise, which produces a sad phase. And sad phase is negative. So that's one way to look at it. Okay. Well, thank you very much. Hopefully this will upload nicely. And it's been 36 minutes me explaining one problem. Hopefully it was done nice and slow enough for you to pretty much get the main idea. So don't worry. I'll get more efficient and we'll get better. Thank you.